Ever wondered about the different types of forces in physics? Forces, the invisible hands that shape our universe, are fundamental to understanding the physical world around us. They dictate the motion of planets and the flight of a frisbee, the pull of gravity and the push of a gust of wind. They are the unseen actors behind every action and reaction. Physics at its heart is a study of these forces and their effects. So, ready to explore? Let's delve into the various types of forces and their respective formulas. First, let's talk about gravitational force. This is the attractive force between two objects with mass. The formula is gravitational force equals the gravitational constant times the product of the two masses, all divided by the square of the distance between their centers of mass. In simpler terms, it means that everything pulls on everything else in the universe. However, the force becomes weaker the further the objects are from each other. Next up, we have the centrifugal force. Centrifugal force, ever heard of it? This is the force that keeps objects moving in a circular path. Imagine twirling a ball on a string. It's the force that pulls the ball outward. The formula for centrifugal force is the mass of the object times the square of its velocity, all divided by the distance from the center of the circle. So, in essence, it's the mass times the velocity squared over the radius. Moving on, let's discuss the force of uniform linear motion. Force of uniform linear motion sounds complex, doesn't it? But it's rather simple. This force is what keeps an object moving at a constant speed in a straight line. The formula is F equals ma, where F is the net force acting on the object, m is the mass of the object, and a is its acceleration. However, in uniform linear motion, the acceleration is zero, so the net force is also zero, maintaining a constant speed. Next, we'll look at the braking force. Braking force, a concept familiar to drivers. This is the force that brings moving objects to a halt or changes their speed to zero. The formula for braking force can vary based on the type of braking employed. For instance, in the case of disc brakes, the formula is force equals negative k times x, where force is the resultant force acting on the disc brake. K is the disc brake's elasticity constant, and x is the displacement of the disc brake position. Let's move to the force on waves. Force on waves, a fascinating aspect of physics. Waves experience force due to their interaction with the medium or another surface. The formula depends on the type of wave and the medium or surface. For instance, for transmission waves in water moving at an angular velocity omega, the formula is 1/2 rho v squared omega, where rho is the water's density. This force is a consequence of the wave's interaction with its surrounding environment. Next, we'll discuss the electrical motion force. Electrical motion force, a key concept in electromagnetism. This force comes into play when an electrically charged particle interacts with an electric or magnetic field. The formula for this force is F equals Q times E, where F represents the force, Q is the charge of the particle, and E is the electric field intensity. Essentially, this force dictates how a charged particle will move within a field, making it a fundamental aspect of physics. Lastly, let's talk about thermal force. Thermal force, a concept that involves temperature changes. Let's delve in. This force arises due to variations in temperature within a system. For an ideal gas system, the formula is represented as negative N, the number of moles times R, the universal gas constant, times T, the temperature, times the partial derivative of temperature with respect to volume. Essentially, it's the force exerted due to the expansion or contraction of a substance in response to heating or cooling. This concludes our discussion on the different types of forces. We've covered a lot of ground today, haven't we? From the gravitational pull between two masses to the centrifugal force in circular motion. We've delved into the force of uniform linear motion, the braking force that brings objects to a halt, and the force on waves due to their interaction with their medium. We've also explored electrical motion force and thermal force. Remember, each force has its unique formula, and understanding them can significantly boost your grasp of physics. Keep exploring and keep learning.
Ever wondered how different forces work in physics? how they interact to shape the world around us. Today we delve into the intricate world of forces, the invisible hands that sculpt the universe. Consider Newton's laws of motion. First, the law of inertia. A body at rest tends to stay at rest, and a body in motion tends to stay in motion. No mathematical formula for this one, but it's a fundamental principle that lays the groundwork for understanding forces. Then, Newton's second law, force equals mass times acceleration, or F equals ma. Force is measured in newtons, mass in kilograms, and acceleration in meters per second squared. Newton's third law? Every action has an equal and opposite reaction. Again, no specific formula, but an essential concept that defines the nature of forces. Next, the gravitational force, defined by Newton's universal law of gravitation. Force equals the gravitational constant times the product of two masses, divided by the distance between them squared. Then, we have the electromagnetic force governed by Coulomb's law for static cases. Force equals Coulomb's constant times the product of two electric charges, divided by the distance between them squared. Frictional force depends on the context, but generally, it's the product of the coefficient of friction and the normal force. Centripetal force, that's mass times velocity squared divided by the radius of the path. The force exerted by a spring is explained by Hooke's law. Force equals the spring constant times the displacement from equilibrium. Buoyancy, or the buoyant force, equals the density of the fluid times the volume of the fluid displaced, times the acceleration due to gravity. The Lorentz force involves electric and magnetic fields. It equals the electric charge times the sum of the electric field and the cross product of velocity and magnetic field. In hydraulic systems, force is calculated based on Pascal's principle. If a force is applied to one area, the output force on another area is the input force times the ratio of the areas. Finally, the force exerted by a photon, such as in radiation pressure, is calculated using the momentum of the photon. However, this is generally very small. In summary, forces in physics are complex and varied, each governed by its own set of principles and mathematical formulas. From Newton's laws of motion to the forces exerted by photons, understanding these forces brings us closer to understanding the fundamental workings of our universe.